Welcome to this lesson. I want to do an overview of what this lesson is about as well as what kind of this entire unit is about. So throughout this unit, we're going to be working with systems of linear equations. And what a system of linear equations is a set of equations in two or more variables where we want all the equations to be true at the same time. So it's a very simple example. Suppose I said two numbers add up to 2, but those two numbers' difference is 0. What are the two numbers? And so we want to look at different strategies to figure that out. So in that simple example, we probably kind of know at least one solution that 1 and 1 should work. 1 plus 1 is 2 and 1 minus 1 is 0. But are there other answers that might work? So that's what we want to be able to look at, is we want to find graphical ways of solving that, as well as algebraic ways of solving that type of problem. And then we also want to kind of see where else might this reasoning be useful. So the basic structure we're going to go with is we're going to start off learning how to solve homeworky type problems, where we're going to give you a system of linear equations, just say solve it. And so we're going to start off with 2 equations that have 2 unknowns. In a later lesson, we'll move on to 3 equations with 3 unknowns, and then we'll start looking at applications, at word problems, to say, realistically, where is this going to come up at? What real-life situation would lead to problems like this? So focus back on this particular lesson. What we're going to do in this lesson is we're going to look at 3 different strategies for solving systems of linear equations in 2 variables. Those 3 methods are going to be to solve them graphically, to use substitution, and to use the addition method, which is sometimes called the elimination method, but we're going to try to stick to calling it the addition method. So again, that's the graphing method, the substitution method, and the addition method. Now, just fair warning, when it comes to our actual exam over this material, you will be tested on each of these 3 methods. So the directions are going to be really important. I'm going to say solve this using graphing or solve this using substitution. You need to identify which of those it is, which also means that you need to show your work. So you need to show your steps of what you did so you can show me that you understand the process. And basically the reason behind this is the strategies are important. They're good problem-solving skills. And we come up with answers using technology. That's not really the goal. The goal is to learn these methods because then we can apply them in other situations as well. So that's kind of the idea on why I want to test you on these methods. You want to make sure that you do understand each of the 3 methods. And that's what we're going to look at in this lesson, is we're going to go through each of those 3 different methods, why we'd want the 3 different methods, why isn't there just one great one, and we're going to look at that. And then on the exam, there will be questions where I just kind of say, hey, do whatever you want on this one. Just show me some work. So it's going to be up to you to decide, all right, what's the best method in this case? With that said, let's get into our first example and what these systems are going to look like and how we're going to solve using graphing. Solving a system of linear equations by graphing. So the first system we're going to look at is y equals 2x plus 1 and y equals 4 minus x. And so now remember that the basic idea here is that we're looking for the solution to be the point or points that make both of those equations true at the same time. We want to find their overlap. So what I want you to think about is, as far as graphing is concerned, now taking a step back, the big idea of graphing is to get an overall understanding of what a solution to a system of equations is, to consider the big picture. That's really what we want to do here. So when we think about the line y equals 2x plus 1, and we graph that using a slope of 2, y-intercept of 1, what we're actually doing is we're plotting all the ordered pairs that satisfy the equation. There's an infinite number of ordered pairs that make that equation true. Same thing when we're graphing y equals 4 minus x. We're graphing all the ordered pairs, the infinite number of ordered pairs that make that equation true. So let's go ahead and do that. Let's graph each of those. I'm going to actually use different colors just so it's easier to see which is which and how to refer to them. So I'm going to use blue to represent y equals 2x plus 1. And so again, remember that that means that our slope is 2 and our y-intercept is 1. So that means we're going to start at the ordered pair 0, 1, that's our y-intercept, and we're going to go up by 2, right by 1, up by 2, right by 1, and we can do that a few times, and I'd advise doing it a few times. We can also go down 2, left by 1, down 2, left 1. And do that a few times until you get all the way to the end of the graph, really. The more ordered pairs, the better. And then we're going to connect the dots. And there's our line. So that's the one line. There's an infinite number of ordered pairs there. All of them are solutions to y equals 2x plus 1. Then we want to do y equals 4 minus x. Now this is written in the kind of reverse order, so don't get fooled by that. Realize that your slope is the coefficient of your x, the coefficient being -1. The y-intercept is the constant, so in this case it's 4. So for the red line, we have a y-intercept of 4, so that's where we start. And the slope of -1 says to go down 1, right 1, down 1, right 1, down 1, right 1. Now for this second line, we probably don't need as many ordered pairs, and I'll get into why in just a moment. So we go ahead and graph those. And again, there's an infinite number of ordered pairs there because besides the ones I put dots on, all the stuff in between, anywhere where there's red ink, that's a solution to y equals 4 minus x. So now we're going to take a step back for a second and look at big picture what's going on. Our goal here was to try to find the ordered pair or ordered pairs that satisfy both equations at the same time. The blue stuff is what satisfied the blue equation. The red stuff is what satisfied the red equation. So what we're looking for is an ordered pair that has both blue and red on it. That ordered pair would be the intersection. So that would be the ordered pair 1, 3. That's what the solution to the system actually is. It's the ordered pair 1, 3. The fact that we have a graph in front of us, that was basically our work. We were trying to figure out where that solution was going to be. We drew graphs to figure out where that intersection was. That intersection is the solution. So the solution is 1, 3. We could check this solution by plugging it into both equations and making sure it's true in both equations. So if I put the 3 in for y and the 1 in for x, I should end up with a true statement. 3 equals 3. And same thing for the second equation. If I put the 3 in for the y and 1 in for the x, I should end up with a true statement. And sure enough, it's true for both, so I know that 1, 3 is in fact the true solution to this system of linear equations. So I mentioned during the last example that the whole purpose of solving by graphing is really more about the overall view of solving a system. And so this table right here is just sort of to lay out what could possibly happen when talking about solving a system of linear equations. And we can picture it graphically then. So what we did already see is that you can have exactly one solution. And that's what we saw in the first example, is we had these two lines who had different slopes. There were different lines, they crossed once, there was one answer, and that was it. And the type of answer to expect then is a single ordered pair. Now there's other things that can happen though. So we could have one line right here and the second line be right on top of it. So if your slope is the same and your y-intercept is the same, so that your two lines are really the same line, then you want to say, all right, well, where do these lines cross at? Well, they're crossing all the time. So there's an infinite number of solutions. Now, the way that we write that answer, you can see in the third column of the table over there, is what we call set builder notation. Now, that's read as the set of all ordered pairs xy such that ax plus by equals c. Now, the ax plus by equals c part of this is whatever the equation is that we graphed. So if this was y equals 2x plus 1, then we can put that there. Now it's typically written in standard form there, but it's not completely necessary. But set builder notation is a way of writing an infinite number of ordered pairs. So I do want to point out with this infinite number of solutions thing that we're not going to say all real numbers. Because if we look back to the situation that we have these two lines that are on top of each other, if we think about what the actual solutions are, they're ordered pairs. They're things like 1, 1, 2, 2, 3, 3. To say all real numbers would be to say 5 is an answer. And 5 doesn't even make sense. It's not in the right ballpark because of the fact that we're trying to look at ordered pairs, not numbers. Similarly, we don't want to say all ordered pairs work because this ordered pair over here doesn't work. He's not part of the intersection of those two lines. That's why we need that set builder notation. Because even though there's an infinite number of solutions, there's a specific set that are the solutions that are where they overlap at. All right? Now, the other case that can come up is that we could have two lines that are parallel. So if we have two lines that are parallel, we know they're parallel if their slopes are the same and their y-intercepts are different, then we're going to say there's no solution. So we can also sometimes call it the empty set. We do that empty set symbol. So those two lines never cross. Therefore, there's no solution. Now, I bring these situations up because in a little bit, we're going to get into talking about how to algebraically solve a system of linear equations. And we're going to run into these situations. We're going to run into an infinite number of solutions or no solutions at all. And we want to make sure we understand, all right, why would that happen in the first place? And so we can visually see it by thinking about these graphically to say, if they're literally the same line, we're going to get an infinite number of solutions. If they're parallel, there's zero solutions. But if they're in any way, shape, or form different lines that have different slopes, they're going to cross once and that's it. We're never going to have two crossings because in order to cross back, I would have to bend somehow. And we're only talking about linear equations, straight lines. So there's no way that we can get like exactly two answers or anything like that. There's only infinite, 0, and 1. So let's take a look at this example here. So you can see this is actually an example intro, and that's for a good reason. We want to try to solve this system of linear equations graphically. So to solve it graphically, we want to graph each of these lines. So let's take a look at this first one, and we'll do it in blue. It has a y-intercept of 4 and a slope of 1/3, meaning to go up 1 over 3, up 1 over 3, up 1 over 3, or down 1, left 3, down 1, left 3, down 1, left 3. Pretty easy equation to graph. It was in y equals mx plus b form. We had a nice, happy, whole number intercept. Beautiful. Nice and simple. Let's go ahead and graph the other one, which also looks like a very simple linear equation to graph. Y equals 5x plus 3. We've got ourselves a y-intercept of 3 to start off at, and a slope of 5, which means to go up by 5, right by 1. So if I go up by 5, right by 1, and I connect those dots, where do I cross at? Where's the intersection? Let me zoom in. It's kind of hard to tell. As far as the x value, it's somewhere between 0 and 1. Looks like it's a little bit smaller than a half, so maybe around a quarter or so. Maybe 0.2, maybe 0.15. How about the y value? The y value looks just a tiny bit above 4. I don't know, maybe 4.05, 4.1, I don't know. That's the problem with the graphing method. The graphing method will allow you to visualize what your answer is, where the intersection is, but unless that intersection is at a nice, happy, integer-ordered pair, the answer doesn't really work for us. So at this one where we're at some sort of fraction-y value, I have no idea what it is. I mean, I have an idea, but I can't get a good exact answer from this graph. That's the motivation for why we need to look at algebraic methods of solving these. Graphing only really allows us to visualize what's going on. It doesn't really help all the time for getting an answer. We can get answers if they're nice, happy, integer-ordered pairs, but oftentimes we got to resort to an algebraic method. So that's what we want to look at in our next example. Is let's look at an algebraic method. So the first algebraic method I want to look at is called the substitution method. So I got some steps written out here, and we'll go through them in just a moment. It's going to be more obvious as we go through the actual example itself. But our steps through here are basically going to be, in both algebraic methods, a way of taking a system that has two equations, two unknowns, and to somehow boil it down to only have one equation with one unknown. If we can solve the one equation, one unknown, then we can take the answer to that and plug it back in to figure out the other unknown. That's going to be our overall goal of both methods. And we're just going to look at two different ways of approaching it. For this substitution method, and we'll see why it's called the substitution method in just a moment, our first step is going to be to solve one of the equations for one of its variables, which means we have four options. We could either choose to solve to get the x in the first equation by itself, or we could solve to get the y in the first equation by itself, or we could get the x in the second equation by itself, or we could get the y in the second equation by itself. Now you'll note I have a hint here. The hint is to look for a variable that has a coefficient of 1 or -1. In our example, that would be the y in the second equation. That one has a coefficient of 1. So that's what we actually want to solve for. The reason for that is that's going to help us to avoid fractions. Because suppose we try to solve for the x in the second equation. If I try to get the x by itself, then as soon as I divide by -3, as soon as I divide by its coefficient, I would be introducing a fraction into the problem. Whereas if I only have a coefficient of 1 or -1, then when I divide by that coefficient, when you divide by 1, you're not introducing a fraction into the problem. So that's why we want to look for a variable that has a coefficient of 1 or -1 when we're using the substitution method, because that's going to allow us to avoid fractions. And as we know, fractions suck. Step 2. So once we have one of the variables solved for, we're going to plug it back in to the other equation. So we're basically going to replace all the y's in the first equation with something in terms of x. And that way we have an equation that only has x in it. We can then solve that equation, and now we know the answer for x. Once we have an answer for x, we can plug that answer for x back into one of the other equations and get an answer for y, which means we've got an ordered pair. We've got the answer. We can check that answer back in the original. That's our plan. Let's see it in action now. So we already said we were going to take a look at the second equation and solve it for y. We would do that by adding the 3x to the other side. You'll notice that I put a star next to the equation that I'm solving for. The reason I do that is that I remember I've used that equation. When I plug this guy back into the other one, I need to know which is the other one. I don't want to plug back into myself. Because that's our next step. Now that we know that y equals 3x plus 6, our next step is to take this and plug it back in to that equation right there. So what we've got to do here, let's take a step back and see what's going on. Y equals 3x plus 6. What does that mean? That means y is the same thing as 3x plus 6. They're identical. So that means anywhere in my problem where there's a y, I could replace it with 3x plus 6 because they're the same thing. And that's why this is called the substitution method. We're going to substitute 3x plus 6 anywhere that we see a y in that first equation. So that first equation is 7x minus 3. Now instead of y, we're going to write 3x plus 6 because they're the same thing. And now we have an equation that only has x's in it, which means we can solve this equation. If I distribute that -3, then I combine like terms, then I can add the 18 to the other side, and then divide by -2. Now I have my answer for x. Once I have my answer for x, I'm going to plug that answer back into one of the other equations in order to solve for y. Because then I have y equals 3 times, now instead of x, I have -2. 3 times -2 is -6, and -6 plus 6 is 0. I now have an ordered pair. I know that my solution has an x value of -2 and a y value of 0. Now it's a good idea to check your solutions. So in the first equation, if I plug -2 in for the x and 0 in for the y, I get a true statement. Now it needs to work in the second equation too. So if I replace the x with -2 and the y with 0, hey, it works there too. So -2, 0 is in fact the correct solution to this system of linear equations. And this is the substitution method. So let's look at another example of solving by substitution. So the hint, remember, is that we want to look for a variable that has a coefficient of 1 or -1. So as we look at this problem, it looks like the x in that equation is a smart idea. So we're going to try to get that one by itself. And so again, I'm going to put my little note to myself that I'm using the first equation. That way, when I plug it back in, once I solve for x, I plug it into the second. Because if we think about it, if we work with that first equation, if we think about it graphically and he's a line, if I plug him back into himself, I'm looking at where he crosses himself. I'm always going to find that it's an infinite number of solutions. Whereas if I have the line that's the first one, if I plug him into the second, I'm saying where does my x value cross this one at? Oh, it's right there. So that's our idea of the substitution method, is we're trying to see where those lines cross at. So back to our problem here, we're going to go ahead and subtract the 1 to the other side. Then we'll multiply by -1 to both sides, telling us that x equals 2y plus 1. We're then going to go ahead and plug this back into the second equation. So that everywhere in that second equation where there's an x, we'll replace it with a 2y plus 1. So we'll replace that with 2y plus 1 minus the 3y equals 4. So now we have one equation, one unknown. We'll go ahead and distribute the 2. We'll combine like terms. And then we'll subtract the 2 to the other side. Now that we know what y is equal to, we plug it back into the substitution equation. You could plug it into either of the two original equations as well, but this is actually the beauty of the substitution method. We found what y is, and our goal is now to solve what x is, and we already have an equation that's x equals. So that kind of makes it easy. So we have x equals 2 times, instead of y, we're going to use the value of y. So we have x equals 4 plus 1, or x equals 5. So this means that our solution has an x value of 5 and a y value of 2. So remember that you're writing ordered pairs, and so the order matters. We do always write the x value first, followed by the y value. And then we should, of course, check our answers as well. So if we check equation 1, we replace the x's with a 5, replace the y's with a 2. 1 minus 5 is -4. -2 times 2 is -4. That checks out. With equation 2, we have 2 times the x value minus 3 times the y value is supposed to equal 4. That's 10 minus 6 is 4. That checks out as well. So 5, 2 is in fact the correct answer. All right, so here's example 4. With example 4 here, we're again looking for a variable that has a coefficient of 1 or -1. So I do notice a variable that has a coefficient of 1 right there. So that's what we're going to solve for. We're going to solve for the x in the second equation. Pretty easy to solve for. We're just going to add the 8y to the other side. That gives us 8y plus 4. Now that we have x equals, we're going to substitute this back into the other equation. Remember, it's always the other equation for what you use to solve. So we're going to replace every x in that equation with 8y plus 4. So we had 1/4 times x. Now instead of x, we're going to use 8y plus 4. Then it was minus 2y equals 1. Now we can distribute the 1/4. We could clear the fractions if we wanted as well. But since everything's divisible by 4 within that parenthesis, we may as well just distribute. That's going to give us 2y plus 1 minus 2y equals 1. Now 2y minus 2y is 0, so that leaves us with 1 equals 1. Hold on a second. Our variables are gone. What just happened there? Well, let's take a step back. We were trying to figure out at what y value do those two lines cross. That's what we were solving when we got down to one equation, one unknown, is what y value is it when my two lines cross? And we found 1 equals 1, which back with linear equations told us that there was an infinite number of solutions, that it was all real numbers. Now, with a one variable situation, it is all real numbers. Remember, that's not our answer here. What that tells us is every y value works. Our lines are crossing at every possible y value. Now, that doesn't mean all real numbers work. It doesn't mean all ordered pairs work. What it means is I've got the same line twice. So there we go. Same line twice. At every y value, there's a crossing. That's what's going on here, is these are the same line. So the way we write this answer is we write it in set builder notation with a set of all ordered pairs x, y such that, and then you can write either one of the equations. Now, here's the cool thing. So a lot of times it's kind of hard to check your answer in a situation like this. If we know that these are the same two lines, they should look the same. You could get them both into y equals mx plus b form if you wanted as a way to check your answer. Now, we could also, in this particular case, from the original problem, we could multiply both sides of that first equation by 4. And hey, look, it matches up to the original second equation. So of course, if the two equations look identical, then they are the same line. And that's what's going on here. But I want to make sure I show this example to point out algebraically what it's going to look like when we have an infinite number of solutions. So when you get down to one equation, one unknown, and you get something like 1 equals 1, 5 equals 5, 0 equals 0, something like that, that's going to tell you there's an infinite number of solutions. Now, it's really, really important that you had done the work prior to that correctly. That, for instance, if we would have taken our substitution equation and plug it back into itself, you're always going to get a 1 equals 1 or 0 equals 0 situation. So we got to be careful there. We got to make sure that we're plugging our substitution equation back into the other equation. That's really, really, really important. So 1 equals 1, again, remember, or 5 equals 5, 0 equals 0 means there's an infinite number of solutions. Now, if, on the other hand, you ran into a situation like 0 equals 1, 0 equals 5, 10 equals 7, that means there's no solution because that's a false statement. That's when your two lines are parallel. So there's no solution if you end up with a false statement like 0 equals 1, 5 equals 2, something like that. All right, so earlier in this lesson, I talked about how the fact that we're going to have a couple different algebraic methods of solving these systems. And at this point, you might have said, all right, well, why? That substitution method seems all well and good. We're getting all sorts of great answers. We can solve all these problems. Why do we need something beyond substitution? So I want to take a minute to show you why there might be better ways to solve these than substitution. So let's take a look at this particular problem here. Well, in this system, our first step is supposed to be to look for a variable that has a coefficient of 1 or -1, and there isn't one. So my suggestion, if there isn't one, is find the smallest coefficient. So let's go ahead and solve for this guy. And basically the idea is when we solve for him, we're eventually going to have to divide by the coefficient, and that's what's going to introduce fractions into our problem. So we may as well have the smallest denominator possible. So we're using the first equation to solve for a variable. So we're going to subtract the 5y to the other side, and then we're going to divide by the 3. And so we can see there's fractions in this problem. Bummer. Now let's do the substitution. let's plug the x into the second equation. So everywhere where there's an x, we're going to replace it with negative 5/3 y plus 7/3. So we have 7x, but instead of x, we're going to put negative 5/3 y plus 7/3 minus 4y equals 1. All right, now we're going to distribute that 7. That big sigh tells you, I don't really want to do this. This is ugly. So we're getting 49/3 there, minus 4y equals 1. At this point, I'm going to say, you know what? I don't want to deal with these fractions anymore. Let's clear them. Let's multiply both sides of the equation by a 3. That's going to get us negative 35y plus 49 minus 12y equals 3. We combine like terms to get negative 47y plus 49 equals 3. Negative 47y. Now let's subtract this over. Got negative 46. So y is 46/47. Now, let's plug this 46/47 in over here to get x equals negative 5/3 times 46/47 plus 7/3. I'm not going to finish this out. This is getting ridiculous. The cool thing is, with the next method that I'm about to teach you, problems like this, even if they end up having some kind of crazy fraction-y answers, aren't going to be this bad right here. That's the beauty of the other method. So let's go ahead and look at that example. The first example I want to look at with the addition method is not going to be as complicated as that one we were just looking at. I do want to start off with one that's much simpler, much more straightforward. Then we'll kind of get into the steps that goes about it. Now, one thing that we got to be careful with here, so I want to start off talking about a step that might not seem altogether intuitive, but it's completely legal, and we'll see how it helps us and why it's legal. Now, what I want to do here is I want to go ahead and add the left side of equation 1 to the left side of equation 2, and I want to add the right side of equation 1 and the right side of equation 2 together. So before I show that work, I do want to point out that this is perfectly mathematically legal. This is something you probably haven't done before. There's not really been a need for it. But I want to point it out using a very simple demonstration. So equations were probably first introduced to you as balance scales. So if you think about a balance scale where we've got kind of a basket on each side, and in order for them to be balanced, they have to have the same amount of weight in them. So I'm not a good artist by any stretch of the imagination. This is my version of a balance scale. We got a little fulcrum there in the middle, and we have a bar, kind of like a teeter-totter, that's going to keep them balanced. And so suppose I tell you that I have a square on one side and two triangles on the other. And I tell you, hey, they're balanced. We're good. And I have a whole separate balance scale over here. And I have two circles over here, and let's go ahead and say one diamond over here. And I tell you they're balanced too. So if these are balanced, then wouldn't it be true that if I have a square and my two triangles, I'm still balanced? And if I put my two circles and my diamond, it should still be balanced. So all I did is I took everything that's on the left of either one and put it down there at the bottom. Took everything that's on the right of either one and put it together. And if both of the original ones were balanced, the bottom one's balanced too. So if you can visualize that, then we can go back to our equation and say it's okay to add the left sides together and the right sides together, and that's going to get me a new equation. And that's exactly what we're going to do for what's called the addition method. In the addition method, we're going to be adding things together in order to eliminate a variable. So now take a step back again. And if you remember when I was talking about the various algebraic methods, I said both of them that we're going to talk about have the same overall goal. And that overall goal is to start with 2 equations, 2 unknowns, and do something until we're down to 1 equation, 1 unknown. With the addition method, if I add together x plus x is 2x, and y plus negative y is 0. 7 plus 5 is 12. So that's how we can kind of get rid of a variable or get this down to 1 equation, 1 unknown, is because of the fact that y plus negative y was 0. So this first example I kind of handpicked. I made it what I like to call the perfect scenario. Everything worked out nice. We add together. The y is gone. Now it's easy. Divide both sides by 2. My x value is 6. Now that I know my x value is 6, I can plug this back into either one of the original equations. Doesn't matter. I get 6 plus y equals 7, so y must be 1. And I've got myself an answer. 6, 1. It's an easy answer to check. First equation, 6 plus 1 is 7. Second equation, 6 minus 1 is 5. We're all good. That is, in fact, the correct answer of 6, 1. So, something to think about as I kind of wrap up this example here is you need to look at this example and say, why was this one so easy? What made it work that when I added them together, the y's went away? Well, the y's were opposites. That's what we want. So we're going to, in the next example, talk about the steps that we're going to go through for taking care of these types of problems, for solving using the addition method. But we're going to keep in mind, no matter what we do, no matter what steps you throw on something, your basic goal is to have opposites that you're adding together. That way they go away. All right, so this next example is not the perfect setup. It's not the perfect scenario. I want to point that out, so don't copy down what I'm about to write down. If you were to try the same thing as what we did in the last example and just add these together, you're going to get negative 3x plus 4y equals negative 2. That's not helpful. Our goal in using the addition method is to get rid of one of the variables. It's to start with 2 equations, 2 unknowns, and end with 1 equation, 1 unknown that we can solve. So that's not helpful. So I'm going to erase this and go back to the drawing board. And what we got to think about is that we want our variables from the 2 different equations to be opposites of one another. So our very first step we want to do is we want to multiply the equation or equations by a variable, or a value that will cause the coefficients of one of the variables to be opposites of each other. So as we're looking at this, we have 2 options, and neither one's right or wrong. We could make the x's opposites by multiplying the second one by negative 2. That would make them opposites of one another. Or we could look at the y's and say I could multiply the first equation by negative 3, and that would make them opposites of one another. It doesn't matter which one you do. I'm going to go ahead and multiply by negative 2 in the second equation. Now, when I do that, I'm going to rewrite the entire system. Remember, the system stays together right now. So I'm just going to rewrite the first equation. Negative 2x plus y equals 2. And as I distribute the negative 2 across the second equation, I'm going to get positive 2x, negative 6y equals positive 8. Now my x's are opposites of each other. So now we can do what we did in that simple example. Step 2, we want to add the equations together. So let's add. Negative 2x plus 2x is 0. Y plus negative 6y is negative 5y. And 8 plus 2 is 10. Now we can very simply solve this equation. We get y equals negative 2. Now we want to take this value of negative 2 and plug it back into any equation up there. Now, personally, I would kind of keep in mind that my goal is to solve for x, because I already know what y is. So I would look for one of the equations that looks like it's easy to solve for for x. So I'm going to plug back in over here where I have negative x plus 3 times the value of y is negative 2, equals negative 4. And we're just going to solve this equation. Add the 6 to the other side, multiply by negative 1. And so we get an answer of negative 2 for the x, negative 2 for the y. And just like always, it's a good idea to check your answers. In the interest of time, I'm not going to show that, but definitely take the time to check your answers by plugging that x and y back into both equations. And remember that when checking, you have to plug into both equations, not just one or the other. Because if you only plug it into one, all you're saying is this ordered pair is on one of the lines. You need to plug it into both, so you can say it's on both lines, which means it's the intersection. All right, so in this example, this is going to be our most challenging example. Our answers are going to be kind of ugly fractions. And so I want to show this example to show you a nice strategy to not have to worry about crazy fraction answers. And that's actually the beauty of using this addition method. Now, as I look at this, we got to say, all right, well, I need to somehow make my x's opposites or else my y's opposites. If I want to make the x's opposites, I can't simply multiply 4 by something to make it up to 6 without being a fraction. Similarly, I can't look at the y's and say I can't multiply 5 by something to bring it up to 6 without making some fractions. What I can do, though, is I can multiply both equations by something to make the values match up. So, for instance, with the x's, if I want to get those guys to match up, I could bring them both up to 12s. So I could multiply the first equation by a 2 and the second equation by a 3, and that would bring both of the x's up to 12x. Now, I got to be careful, though, because I actually want them to be opposites. Not right now, they're both 12x. I want one of them to be negative 12x. So I need to change the sign of one of these. Currently, for the y's, we're looking at negative 10y and negative 18y. So let's go ahead and make the bigger one positive. So let's change the sign of the 3 there. Let's check out what this looks like for both equations. We're going to distribute the 2 across the first to get 12x minus 10y equals 14. We're going to distribute negative 3 across the second. That's going to get us negative 12x, positive 18y, and negative 21. Okay. Now we're set to add these together. 18y minus 10y is 8y. Negative 21 plus 14 is negative 7. I get negative 7/8 for my y. Now, one of the things I really want to point out here that's really cool about this is we do have a fraction answer for y, but we never had to deal with fractions. The fraction didn't come in until we said, all right, I got this negative 7 on the right, divide by 8, bam, there's a fraction. We didn't actually have to deal with fractions. That's kind of cool. Now, if we go through our normal steps, we'd plug this negative 7/8 back into one of those equations, and then at that point we'd have to deal with fractions. That kind of sucks. But I'm going to point out that we don't really have to do that. We could start back at the original problem. And if you look at what we did do, we eliminated the x's originally, and that allowed us to solve for y. We could go back to the original problem and eliminate the y's and solve for the x. And that's actually what I would suggest that you do in a problem like this. Let's rewrite the original problem. But now instead of multiplying by something to get rid of the x's, let's multiply by something to get rid of the y's. If I brought the y's both up to 30s, well, right now they're negative 30, so I need to make one of those guys positive, one to be negative. So let's go ahead and change the sign of that one. Let's distribute those across and see what we get. We get 36x minus 30y equals 42. We get negative 20x plus 30y equals negative 35. Now when I add these together, I'm going to get 16x 0y equals 7. Divide by 16, and I get 7/16. I now have the ordered pair 7/16 negative 7/8. Very gross looking fractions, and I never had to deal with fractions anywhere in the problem. That's pretty cool. So that's one of the cool things about this addition method, is that we can have this answer that has crazy fractions and never deal with fractions throughout the problem. Pretty cool.